Hello students, welcome to this new lecture of machine learning and Python lecture series. I welcome you all to this new lecture, and in this video we are going to talk about linear regression. So we'll not just see the implementation of it, but we'll also see the theory part of it, the maths behind linear regression and the coding implementation of linear regression as well. So today we will be discussing our first machine learning algorithm with linear regression. Right. So we will first, as I said, we will discuss it in theory, and then we will go and implement the same thing into the coding. That's what we are looking into do. So I will simply, just tell you what exactly linear regression is, how to proceed with this, and I'll also give you an idea how can you do the same thing. Okay. I will give you the all the information that you need to understand the linear regression. And basically it's regression part, right? We had seen in machine learning. In machine learning there are three parts, right? First one was supervised learning, supervised, unsupervised, and reinforcement, right? So supervised, unsupervised, and reinforcement learning we have in here. And so basically in supervised, we had discussed there are two types of things. First one is the classification, right? And the second one is regression. There is something else called association rule mining that we hardly use these days. And so basically these are the classification and regression we have classified our data into, our tasks into. So first we are going to discuss the classification, right? Regression. So regression is what is exactly regression we have already gone through. So if you're predicting, let's say, some continuous numerical variable, right? If you're predicting some continuous numerical variable, if you're going to predict a continuous numerical variable, then you have to then that is a particular regression task. If you are predicting the category and our classes are nominal values. Okay. Nominal means categories itself. Okay. Classes or categories. All right. So if you're going to predict something like this, then that is a classification. Otherwise, it's a regression. If you're continuous numerical value, if you're going to predict, I'll just give one example. For example, let's say there is a temperature, right? Let's say you are predicting the temperature. So if the temperature, let's say you say in between 0 to 25 degree for India, let's say 25 degree. So it is cool, we can say, right? It's cool or cold, right? And anything between 0 to above 25, we can say it's hot, right? But the number can be anything. If you are predicting the exact temperature, for example 19.758, if you are predicting this, then it would be regression, right? Once again, I told you it's a continuous numerical value. This particular thing is not continuous numerical value. The thing that you are predicting, it could be anything in between 0 to 100, right? I mean, there can be a vast range as well, but it could be anything in between. It could also have been 19.757 or 7.9. It could have been anything in between, right? So that's why this is the regression task. But if you're predicting whether it's a cold or hot, then that can be thought of as a classification. Now in classification, it cannot be anything other than cold and hot. It will be cold and hot either, like any of these two will be, right? But in regression, it could be anything, literally any value, right? So that's the main difference that I want to make you understand, and I hope you guys are understanding it. So this is the difference between classification and regression, right? Let's understand, if you're going to predict a line, what exactly is linear? I mean, if you're going to predict a number, how can we do that by a linear regression, right? So let's understand what exactly linear regression is, right? So linear regression is nothing but a technique through which we fit a line on the data. right? And we try to predict the trend, and based on that trend, we try to predict the future values or unknown values as well. You might not understand this, but let me just explain it. So let's say we have some X, we have some Y, right? When I say X means it's input. Okay. Y means output label. All right. So we have some values in here. We have some values in here, right? For example, okay. For example, let's say we are let's say predicting, let's say income, or say salary, and let's say experience, right? Let's say if this is experience, right? The input is experience. If somebody gives you experience, like let's say I have 5-year experience or 5.5-year experience. So what should be my salary, right? So this could be thought of as an input and salary could be thought of as an output. You can also build a model that take salary and gives a that will give as an how much experience someone has. So it depends on what exactly you are developing, right? So it's a kind of a regression task. Both side numbers are there. So this is a continuous number. This is a continuous number. For example, if I plot them, let's say somewhere like this. All right. So this is our, let's say, graph. So I would call it, let's say, salary. And this I can thought of as year of experience, right? So this is experience and this is salary. Now, let's say if you see this, you can simply say that there is a positive trend. It's highly correlated data, right? What happens if I could fit a line into this? Fitting a line means you're trying to create a line that follow the data, right? So tell me which line follow the data. Line 1, line 2, or line 3? Line 2, exactly. Line 2 follows the data, right? In other terms, we can say we are fitting this line on the data. See, if you are fitting a line on it, that's why it is called a linear regression, right? We are trying to fit a line on the data, right? In linear regression, we just create a line that follow the trend in the data. Simple. That's what we do in linear regression, right? But for example, if I ask you, let's say this one is line 1, this one is line 2, as always, this one is line 3. Now tell me which one is better. It's very hard to tell actually, right? Even if you be telling, then you'll be considering some features into that. Maybe it might be your reasoning, but it is very hard to tell which line is, fitting the data better in this case. So the reason is because we need to have some, mathematical value so that we can find that which line is better in this case, right? For example, if we could calculate some value as a score and we can find that we have a score for this, we have a score for this, and we have a score for this. And we can also evaluate like higher a score is better or lower score is better. So for example, if lower score is better, then we can say the one with the least score is the best line, right? Or if the higher score is better, the one with the highest score will be the best. See, just I'm calculating the possibility that what could we do further, okay? And what we have already done, I'll tell you. So there is something called loss. Okay, let's understand what exactly is a loss, right? A loss is nothing but, see, these are nothing but points, right? Let's say this is actual data. We already know the salary and the experience for this both. For example, this is involved in training this, in creating this line. And this is the actual salary and the actual, experience. This would be the experience and this would be the salary. Okay. Now, if I predict the same thing by a line, by this line that I have built, what will happen? this line will not predict the same thing. This line will predict on the line. This line will predict always on the line. For example, if you have created this on this machine learning model, right? And then you are predicting the value, and this is the line actually, and then you are predicting on this x. This is the x value, let's say. If you simply draw a perpendicular line in here on this axis, let's say like this. So this would be where it will cross the x, the line. It will be the corresponding salary. This. Sorry. Yeah, this would be the corresponding salary, or this. It would be the same actually, right? But if you see what is actual salary is this. This is the data that we had actually. And the predicted salary by the model is this. So there is a difference. This is called error. Okay. This is one case. The other case might be, for example, I want to predict, let's say the salary, right, at this particular X. Okay. At this X. So the model will predict this. Okay. Model will predict here, but the actual salary is this. Once again, this is also a difference. But in this case, the difference is what? See, if you are simply calculating, let's say this is x-axis, this is y-axis. For example, this is x1, this is x2. And this call y1 and this this is y2. So let's call it y1 hat and call it y2 hat. Hat means every time if you are using hat means, let's say, predicted value by the model. It's not the actual value. Actual value will always be without hat. Right? For example, this y1 hat and y2 hat, these are the predicted value. And if you write a formula for the error, based on this understanding, let's say, whatever we understood over here, we could write y1 or let's say simple y hat minus y hat minus y. This would be the difference between the data, right? So this would be the error. Okay. So this time, this is the error. What will be the error in here? Y minus y hat. Sorry, y hat minus y. So in this case, let's say if I'm writing y1 minus y1 hat, y2 hat minus y2, which one will be positive and which one will be negative? Let's say call it first, call it second. This is a simple geometry, guys. First one will be negative, exactly, which you see, this y is here. This is a smaller y. This y hat is large. If you do y hat minus y1, okay, if you do y hat minus y1, oh wait, what have I done? Actually, this one should
y2 cap.
Oh dear. Okay, my bad. This one should be y hat and this should be y. Okay. So the y predicted will always be on the line because we are predicting based on this line only. This is our linear regression model. So basically, when we're creating linear regression, it's nothing but we are creating a line. Our linear regression model is nothing but a line, an equation of a line of type y is equals to mx plus c. This is our model. This is our linear regression model. That's what we are going to do. How will it do it? We'll just know in the process. Okay. So this is nothing but linear regression model. If you see here, so which one will be negative? Now, the second one, right? The second one will be negative. So what happens if I want to calculate the whole error of the model? I will simply calculate for each point and add up together, right? So we'll simply summation of I is equals to 0 to n and yi, or let's say y hat I minus yi. Oh, not hat. Okay. So there is a problem in here. For example, we have some error over here. We have some positive error over here. We have some negative over here, some positive error. So what will happen? It will nullify itself. I'm just giving you two scenarios once again. Tell me which model is best. Let's say this model is best, or let's say, sorry, this model is best. So let's say, so if you calculate the error based on this method, let's say this is plus x, this is minus x, this is plus a, this is minus a. If you calculate the error in this case with this formula, what will happen? Just plus x plus a minus a. Everything will be 0. And if you calculate the error in this formula with this, so 0 plus 0 plus 0 plus 0, it will be also 0. So both the cases, we have a 0 error. But which one is a better model? This or this? Like, let's say 1 or 2. 2 is a better model because it is following the data much better, and it has, a truly least error, because this is a wrong formula actually we are using in here. So we need to make a modification in this. What if we do mod of each value, the absolute of each value? If we just take absolute of the each value, then we can simply have, avoid this. So we will have an error of 2x plus 2a in here, right? And in here, we'll still have an error of 0, right? So we have some error over here and we have error 0. So we can finally say that this one is the least error, and it is the best model among these two. It is better model among these two. Similarly, the thing that we are predicting here, so this could be a measurement criteria. We can measure the error with this formula, and we can know that which model is better. If the model has least error, then that model is better. If the model has large error, then that model is worse, right? So that's what we can conclude based on this. So this is called error. This is one of the error formula. There is something else other than this we can do. Other than taking an absolute value, what else we can do to avoid that cancellation of the error? What if we square the values? If we square the values, eventually the value will be larger, but the problem will be solved, isn't it? Right? So that is also another formula of the error. We also call it loss, actually. Error, loss, or cost. Right? All these things we can say. This is a cost function or loss function or error function. Right? So this is one type of error. The other type of error can be what? It could be a squared error. This is absolute error we call. Okay. Absolute error. This is the formula of absolute error. There is a squared error as well. Okay. Squared error is just, we have I is equals to 0 to n y hat I minus y I whole square, right? Just square everything and then add. Take a difference, square everything and then add, right? So this could be. Similarly, here we can also have mean squared, mean absolute error as well, MAE, right? Mean absolute error. Here we can also have mean absolute error, right? So what we will do is mean absolute error. We'll just take a absolute error. Sorry, we'll take absolute error and we'll take mean. Like, let's say if we have n points, we will divide it by n. So it's just multiplied by 1 by n. It will become mean absolute error. That's the formula for it. And you can also calculate the mean squared error. You might have heard the term MSE. It's nothing but the mean squared error. And it could be done by, just multiplying by 1 by n into the formula of squared error. We just take this, multiplied by 1 by n, and we have MSE. Now, to bring back to the same level, since we are squaring it, to bring back to the same level, what we can do? That's called root squared error or root mean squared error, right? That's called RMSE, right? Root mean squared error. Root mean squared error means once you've calculated mean squared error, you can simply take a root of that, root over 2, because you're squaring up, so you can take a root of 2. Okay. So that's what we call root mean squared error. Now all the formulas has been clear and their range as well. If you are calculating absolute error and you are calculating the squared error for the same data and same model, you definitely, your squared error will be larger. So it does not make sense that someone's model is better. So when you are comparing two models with two data, try to calculate the same error that you are calculating, either squared error for both or mean squared error for both. Because when you are dividing mean squared error, so mean squared error is nothing but the average error of one data, 1 point, right? If you understand, this, then that's the, I mean, if you are much into the statistics, then you might be getting this, right? Mean squared error is the mean error of each point. But if you are accumulating all of them, then that will be the squared error of each, I mean, the whole data. So the whole point is that when you are comparing two models, you have to compare the same error of both the models. Okay, that's the point. And you also make sure that their data is also same. For example, if you're testing on the different data, on different range of data, then you must have same data in order to compare. So now you might have understood the logic of loss functions or errors. Okay. Right. So let's understand, how do we exactly get a line like this? How do we exactly get a line like this? That's the process of linear regression, right? So there is an algorithm called gradient descent. Okay, there's a gradient descent algorithm. What we do based on this, we try to find out this line. Okay, gradient descent algorithm is an optimization algorithm. Now let's understand what exactly optimization algorithm does and why do we need in here. Okay. So basically in gradient descent algorithm, first, in order to create a line, in order to find a line that follow the data best, we will create a random line. Okay. So the process of linear regression is, first we will create a random line, right? And then apply gradient descent on that, and it will optimize the line to be the best line of that, right? So we will create a random line, let's say this, and then gradient descent will actually change the weights and biases, weights of the data, and then it will try to make this line make closer to the data, and that follows the actual trend of the data. So that's the same, main thing that we are doing. Okay. We'll randomly create a line and then we'll apply gradient descent. So how do we randomly create a line first? So remember, the equation of a line is what? Y is equals to mx plus c, or ax plus b, you can also say, right? If you have some value of m, you have some value of c, right? If I write, let's say y is equals to 3x plus 4, this is a line, right? This is a line, this is an actual line on the plane, right? We actually randomly choose the line for this. In machine learning, mostly you will see the weights will be taking, will not be taking like M and C. We'll be taking it, and for example, this is our model, so we'll call it y hat, not y. So y hat is equals to w1x plus w0, right? So y hat is equals to w1x plus w0. So this is our line, right? Then this is the equation of a line. Then we randomly select a value for W0 and W1. Okay, W1x plus W0. And then we will randomly generate values of W1 and W0. Now, in the last session, somebody was asking, why do we need to generate random values for? So here we are generating the random values for the weights. Now it's in our hand. For different application, we generate the values of these weights in different range. But normally we generate in the range of 0 and 1, right? So here we will randomly generate weights. Weights means this value of W1 and W0. Now, if we have got a value of W1 and W0, we eventually have a line in here, right? So the equation of a line is fixed. If we randomly generate the value of W0 and W1, so we will have a random line in here, right? Okay. Now, once we have got a line, okay, let's call it W0 and W1x and W0. Then we have to change the value of W1 and W0 so that this line, see, this is the line, right? Let's say we randomly generated this line. Then we have to update its weight. Update its, let's say, M and C, the coefficient and the intercept. M is the coefficient and C is the intercept, right? So we have to, I mean, eventually, if you change this parameter of a line, you will see the line will move, right? If you change C, if you increase C, so eventually line will go up. If you decrease C, the line will go down. If you increase or decrease M, it will rotate, right? So we have 2 degrees of freedom in here. Okay. So that's what we can do with the line. And if it is a line, so it is an endless line. It's not like that it is following till here and starting here and it's ending over here. By changing this M and C, we can actually find an exact line that follow the data like that. All right. So what do we do is we take the help of error and we find a line that will give us the least error. Okay. There are so many optimization methods as well. If you are in the engineering, if you are in the second or third year of engineering, you might have, second year of engineering, you might have gone through a Newton-Raphson method of optimization in your, I guess, M2 or M3, I'm not sure, right? So that is also a method of optimization, right? Gradient descent is another method of optimization. Okay, so let's say, how do we do this in here? So first, we will eventually have a random values for W0 and W1. We have a line y is equals to W1x and W0. And then we calculate loss. Calculate loss. This is the first step that we do. And then after calculating loss, we will take a derivative of this. Partial derivative with respect to W0 and W1. Now, here it comes like which loss function you are using. For example, if you're using absolute error, so there will be different value for that. If you're using squared error, so there will be different value for that, and so on. Okay. So for example, let's say you're using this squared error, right? So what will be the function of the squared error for the loss? Loss is equals to not y1, okay, so let's say y minus y hat, let's say, or y minus y hat, or y hat minus y, anything will do. Okay, so let's say if I have y minus y hat whole square, this is the loss, right? So we are doing for one point, we can replicate it for all the points, right? So this is the loss, right? If we take a partial derivative, so that's what we call okay, before that, I'll just tell you in a nutshell what exactly gradient descent is. Okay, so we will calculate the loss and then we will calculate the delta W. Okay, we will update the weight by using delta W. So we have an equation of W is equals to W minus eta delta W. Okay, so we have W is equals to W minus eta delta W. Okay, this W will be both W1 and W2. So this is how we update the weight, and this weight updation makes sure that we are updating the weight in the right direction, right? If it needs to be increased, it will be increased. If needs to be decreased, it will be decreased. That will be decided by the sign of this delta W. Okay. So we get a loss. So if you are calculating loss, so how this delta W gets calculated? Okay, let's see. Delta W is equals to, we write del of W divided by W. Once again, if it is for W1, it will be W1 over here, both on above and on the top. Sorry, del of loss here, not W. Del of loss divided by del of W. So if you are using, let's say W1, so it will be W1 over here. Okay. Let's say if you are doing for W1, right? Del W1 will be, here you will write your equation of the loss, y minus y hat square divided by del of W1, right? Now you will be writing y minus, what is the formula of y hat? Y hat is nothing but this, W1 and W0. So you will write y hat, y minus W1x plus W0 whole square. Sorry, whole square. If you do, square this value and take a derivative with respect to W1, you will get minus 2x y minus y hat, right? Eventually, you will not get y hat, you will get this W1 x minus W0. So you can replace it with y hat. So this is what you will get if you calculate with respect to W1. And if you calculate the delta W with respect to delta W0, so you will get the same equation. You will get -2. This is, remember, it is X, it is not multiplied by. You will get -2, and then X will not be here, and same thing, Y minus Y hat, right? This will be for W0 and this will be for W1. You can go and calculate the partial derivative and check the results, right? And whatever value you will get, we will put in over here, and the sign of it, right, whether positive or negative, it will decide whether it needs to be added in the weight or it should be decreased. So we will basically do the same thing iteratively. So what will happen? Let's say I'm running it 100 times or 1000 times. I can choose it anything. This is called epochs, right? Epochs means you're feeding your data to the model whole, one epoch means you're feeding the whole data to the model once, right? And you're updating the weight once. So that will be called as a one epoch. So we run it multiple epochs, like 100, thousands, whatever you choose, you can do it. Okay. If you think that is not enough, so you can increase it as well, right? In the next time, right? So that's how we do it, machine learning. Okay. So once we update the weight, this weight will eventually bring the data or the weights as such. This line will actually go and go along with this over here. From here, it will go there, right? This is the main thing in here that happens. There is one term you might be getting new term. This is eta. What is eta? Eta is called learning rate. Okay. Now, learning rate is one of the parameter that is very crucial over here. So basically, see, if you have a weight, see, initially what we have a weight of what? I mean, in the range of 0 and 1, right? Mostly, let's say it's 0.5. And we calculated delta W, and delta W is, let's say, 2. If we do, let's say, -2, what will happen? It will be 1.5 or 1. Let's say 55. Okay. So now we just increase the value of weight. Next time we will have more error, and next time it will be more different, and it will be 10, it will be 20. I mean, it will be increased a lot, right? So that is not a good thing. So in order to avoid this scenario, we take eta as a very, very small value. We know in which direction by the sign we'll be understanding in which direction we have to update the weight, like whether we have to increase or decrease the weight. We will be already knowing that with the help of the sign of this delta W, whether it is negative. Delta W is negative, let's say this. So what will happen in the next iteration? It will be increased or decreased, the W. Let's say Wi plus 1, and this is Wi, this is Wi. This is the same W. W1I is the W, the weight in the previous iteration, and Wi plus 1 in the next iteration. If the value of delta W is negative, what will be the weight in the next iteration? It will be increased or decreased. If it is minus, you put it over here, it is also minus, it will become plus, and then you are doing nothing but, let's say you have a is equals to 5, and you are doing nothing but a is equals to a plus some value, let's say 3. So what will happen? A will become 8 in the next iteration, it will increase. If this negative, if this is positive, then it will be, if this delta W is positive, then here it will be negative, and if it is negative, so it will be decreased. So next iteration it will be 2. It's simple addition, guys. Okay, so it will decrease, not a big deal, right? So let's understand what is the role of this eta. Remember, I told you, if you are increasing or decreasing very large value in the weight, it's a problem for us. Instead of it, what we do, we multiply it very small value. So eta is learning rate. Learning rate decide how slowly or fast we will be learning. I mean, the model will be learning, means model will be updating the weight. We generally keep the value of eta, 0.1 or 0.01 or 0.001 or even smaller, based on the condition or the data that you are dealing with. Okay. If we take very small value, then we'll be able to update the weights to a certain extent, right? Why taking a large value of eta is prohibited, I'll tell you. So for example, let's say if I draw a curve between, let's say error and weight. Let's call it error. This axis is error. This axis is weight, right? If we randomly generate the weight, let's say, yeah, if we randomly generate the weight will be generated in somewhere this range, right? Like, let's call it any range. Okay, 0 to 1 itself. Okay. So let's say we generated over here, let's say 0.9 something, we generated the weight. So what will be the corresponding error? The error will be very, very small, I mean large. Let's say this. It will be very large error. So in order to, this is the error, remember that. This axis is the error. This is the curve of the error. In order to decrease the weight, we need to increase the W or decrease the W. This is the initial W. Let me put it in comparative way. Let's say this is the error E1 and this is the error E2. E1 is lesser or E2? E2 is lesser. So what will be the corresponding W for this? This W1 is lesser or W2? W2 is lesser, because see, when you draw any plot, this is a decreasing, I mean, increasing order, isn't it? Any value here will be always be smaller than any value here. Any value here will always be smaller than any value here. Similarly, if we randomly created the weight and weight is over here, in order to increase, let's say in order to decrease the error, what will we do? We will go this way, and going this way will actually increase the weight. So if you are over here, then we don't know actually what we need to do, right? We have to find a fixed spot. Sometimes this fixed spot will not be here. This fixed spot will be here maybe. Okay. And maybe you have given the weights over here, then you have to increase or decrease. Based on this, you have to increase or decrease. This is the curve, error versus weight curve. Okay. And sometimes this will not only be a convex or concave curve. It can be, there can be local minima. I mean, there can be, this is a global minima, right? If you are aware of the global and local minima, there could be some zigzag path as well. So this is a global minima. This is a local minima. If you are stuck over here, your program can stuck, your gradient descent may stuck over here, right? It will stuck over here and still think that this is the minimum, right? This is the minimum error that we can achieve, right? So in order to avoid this, what we do, we randomly initialize the weight multiple times and we repeat the same algorithm multiple times. And if anyhow the weight generated got this side, then it will go and eventually end up optimizing over here. That's why we call it optimization algorithm. Wherever we generate the weight, it will optimize it. There are some drawbacks. For example, SGD will optimize at the local minima, not at the global minima. But if we randomize the task multiple times and then we record the accuracy, then we can have it, the global minima as well. Okay, so this is the main thing. So now if you have a very large value of, let's say, eta, what will happen? The weight updation will happen very, very fast. The weight updation will happen very, very fast. And let's say I have generated this W and right. Let's say from here, next time the weight has been reduced by a lot and it came over here. Next time it been reduced by a lot, it came over here. And next time it has been reduced a lot and then it came over here. So basically, see, from here to here, it is moving now. Let's remove this step. Okay. Okay. So from here, it came over here and it came over here. Next time, if it is here, the gradient descent algorithm to suggest to increase the weight, and then it will come over there, right? And it will be fluctuating in this space. It may never come over here, but this is the weight that we want somewhere over here. The weight will actually be either this or this, either this or this. It will be fluctuating between this, right? Because we are having a large, eta learning rate. The other case scenario can be that every time you increase, I mean, it can fluctuate. I mean, it could increase like this as well, right? And you will see that your error keep going and going and going every iteration. So that's why we take very small value of eta. If you take very small value of eta, it will take more steps to come. Like it will take small steps, means it will take very, very small change in the eta, in the W, right? And eventually it will come over here, right? So that is the reason why we take very small value of eta or the learning rate. Eventually, we will take more time. It will take more time for algorithm to learn, but it makes sure that your model is learning better and having the better, least error, right? So that's the theory behind it. So in a nutshell, once again, if I explain the gradient descent algorithm in a nutshell, or less linear regression in a nutshell, we will eventually creating a line by w0, y hat is equals to w1 x plus w0, where this will be randomly generated, w1 comma w0 randomly generated, random in 0 comma 1, right? And then we will, what we'll do, we'll calculate loss, right? Get calculate loss. Once we have got the loss, we will calculate delta w minus del of loss divided by del of w. We'll calculate for both w0 and w1. And once we have done that, then we will update the weights, right? W1, let's say w is equals to w minus eta, eta delta w, right? This is what we'll do. And this calculating the loss, and this is an iterative process. Epoch. This is one epoch. This is an iterative process, so we will do it multiple times again and again. Thank you so much for watching this video. If you liked it, do press the like button and subscribe to the channel so that you can never miss the video. And if you want to learn data science and machine learning, do follow my data science and machine learning playlist and hype this video so that it can reach more people like you. Thanks again. We'll see you in the next one. Till then, bye bye and have a great day.